Hey everyone, in this video, I'm going to show you how to deploy an AI RAG application to the cloud. This will make it accessible to everyone else and also enable you to start building a UI or a product on top of it. Now, a lot of you have asked me how to do this, and it's actually quite challenging, especially if you haven't done anything like this before. So just be a little bit patient with yourself, and don't worry if you don't understand everything on the first try. The app we're going to build is going to be a custom AI chatbot for a fictional web design agency that I've made up for testing purposes. We can ask it questions about the services available, the prices, the refund policy, and other details about the business. The source of all of this information is going to be in this PDF file containing all of those details. If you want to change the behavior of the app, you could just modify this PDF file or even add an entirely new PDF altogether. By the end of this project, you're going to have an AI app that is deployed to the cloud, and it's going to be accessible via a public URL endpoint, which means that you can go to the browser to try to use it, or you could pass it along as part of a different application or different UI to use it that way as well. And there's going to be two APIs I can use. So the first one is I can submit a query to the AI application. For example, how much does a landing page cost to design? And then I can execute that. Now, when this API responds, it's not going to give me the answer right away because it's going to send that to another worker function to figure out the answer, because that could take some time. Instead, it's just going to give me this query ID so that I could use to find out the answer later once it's done. And to find the answer, I have this second API endpoint called getQuery. So there I could just paste a query ID that I got earlier from my first call. And then when I execute it, I will have the response. So you could see here, it's actually responded to our question using some information that it's found inside this original PDF. And it's also given us a couple of citations for where it got the source information from. So just to summarize, we're going to host this on AWS, and it will be publicly accessible via an API endpoint. We can use the API to submit any query we want. Both the query and the response then gets saved into a database, and we'll have a separate API that we can use to fetch those results whenever we want as well. Now, as a starting point, I'm going to provide you all the code for the app itself. So that's going to be this initial Python application that interacts with the Chroma database and the AI model. The focus of this tutorial is going to be more towards the deployment of the app, along with the cloud infrastructure you'll need to support it. Eventually, you might want to use this app as a part of a larger service. For example, you might want to add a web UI to it, or turn it into a product by adding authentication and payments. But no matter what it is you want to do, the first step is to give this app an API endpoint to make it accessible. That's why the goal of this video is to create a fully functional API for our AI app that is hosted on the AWS cloud. It might look complex right now, but I'll walk you through every step of the way. We're also going to be using serverless technology to build this, so it's extremely scalable and cheap to run. In my initial estimates using the pricing calculator from AWS, it would cost less than $2 per 1,000 requests. And this is not at all optimized, so you could probably get that cost down by a lot more as well. Now, I'm going to try to make this tutorial as simple as possible, but it's still going to be quite an advanced level tutorial. There's a couple of things I recommend you being familiar with first. Ideally, you'll have experience building a RAG application in Python before, even if it's just running locally as a script. We'll wrap it up with a FastAPI server and put it inside a Docker container so that it can run anywhere. And then we're going to host this on AWS, and we'll use the Cloud Development Kit, or CDK, to write the code for our infrastructure. If you are unfamiliar with any of these topics and want to learn more, then I also have videos on my channel that cover each of them in detail, which I'll link in the description. So if you're ready, let's get started. If you already watched my previous RAG tutorial video, or you're familiar with the concept of a RAG app already, then you can skip the next section. Otherwise, here's a quick recap. RAG stands for Retrieval Augmented Generation, and it's a way to index a data source so that we can combine it with an LLM. This gives us an AI chat experience that can leverage the data. So say I have this PDF file. It's sort of like a customer handbook for a web design business. It's got information like what services are available, how much they cost, and other details about the business, like the project timelines and how you can get help and support. Our app will be able to use this PDF as a data source. So we can ask it questions like, how much does a landing page cost to build? and it should give us an answer that is consistent with that data. Now, this business is entirely fictional, so I deliberately chose to use very weird and specific numbers so that we could test it more easily. Okay, so how does this all work under the hood? Well, first, we have to split the data into small chunks and then transform each of those chunks into an embedding, which is like a vector of numbers. And then we're going to store it into a vector database. Later on, when we want to ask a question, we'll turn our question, or our query, into a vector as well. This will let us fetch the most relevant entries from the database, and we find that by using a function like cosine similarity or Euclidean distance to compare them. We then put all of that together into a prompt and then feed it back to the LLM, and that's how we eventually get our response. To achieve all of this in our project, we first need to generate a database from the PDF. We have a script called populate database to do this for us. It will load the PDF, split it into chunks, and then calculate vector embeddings for each chunk. We can then turn this into a ChromaDB database, which can then be stored on disk. Then, when we want to use this data from our RAG app, we'll just load this from disk. This will let us search the data sorted by relevance to our query text. We then make a prompt with those results and send it to our AI model to get a natural sounding response that will hopefully incorporate that data. So now let's take a look at the code that I've prepared for you to start off at this point of the project. If you go to my GitHub repository, which I'll provide in the link, you'll see the full project, but it's actually got all the features, including the AWS infrastructure as well. If you click here to go to all the commit history, you'll be able to see one of these first commits. This one is called RAG AI project starting point. And you can click here to browse the repository at that point. And now you'll be able to download and clone the repository with just the starting point of the code. So this doesn't have any of the fancy stuff yet. It's just got the core RAG application and the data source that we use. So here I've checked out that code and I've opened up in my code editor, and you should see something like this. All the code is in the source file except this populate database script, which isn't really part of the app, but it's something we run once to create that Chroma database, as you saw earlier. So just looking through the script, it just imports a bunch of stuff, sets a path to that data source that we want, and then where we want to save the database. And you can read through this if you want, but it's not really important right now. I have other videos covering how we build exactly this. So go and watch them first if you want to learn more details about how to build this. And in our data source folder, we actually have this PDF here, which I've just made up for the purpose of testing. It's only a few pages, but it should be enough to give us an idea of how this all works together. You can browse this, you can go ahead and edit this if you want, or you can add even more PDFs to this folder if you want to try out building with your own data source. Now, before you try to run this, set up a Python virtual environment and make sure you pip install all of these requirements first as well. If you need more specific instructions, you should be able to find them all in the README. So let's go to my terminal now and actually run the script to create the Chroma database. Now, I am using an AWS service to get the embeddings for these. So if you're running this and it doesn't work, or you have some AWS credential error, just make sure you set up AWS CLI and enable those AI models first. Now my script's finished running and I've created the Chroma database. So let's go back to our data. And in this file, you see that there's this Chroma folder here. So this is going to be our database. It's ignored from Git because we don't really want to commit it, but we do want to have it here when we use the app. Now to actually run the app, we need to use this query RAG script here. It's got the prompt that we're going to use, and it's got the AI model that we're going to use as well. So if you want to use this, make sure you go to your AWS console and enable this model for your region first. And here's the rest of the code, which again, you don't have to understand what this does yet because that's out of the scope of this video, but this is how we can run it. Now, I just want to show you some other files real quick. We have a helper file to get us the embedding function. And again, as I mentioned, we're using Amazon Bedrock for this. And we also have a file to get us the ChromaDB instance. So this is going to be kind of like a singleton. When we use this once, it's going to get it for us and it's not going to load it again. It's just going to save it into memory the first time we get it. I've split this out into a separate function because later on when we start making it, ready for the cloud, we're going to do different things about how we get our database. Now, this is pretty much the core logic of the app, this query RAG function here. So let's go ahead and test that as well. I've made it so that if you just run the app directly from the command line, you can actually test this with a hard-coded query. However, this app does expect you to run it from this source folder. So if we go to our terminal, we have to navigate to that folder first. And notice that when we run this directly, I've actually hard-coded the question. So if you want to change the question when you test this, you have to change it in the script. Or if you want to be fancy about it, you can add a CLI argument parser here, but that's not what I have. So I'll just go here and run this function. And now you could see the results. It's gone ahead, loaded the database for us that we created. It's found a couple of pieces of information that matches the question. So it's pulled this directly from the document, and then it's turned this into a response for us. And the response is that the cost for a landing page offered by this design agency is $4,820. And it's given us source citations as well. And sure enough, if you go back to the source PDF, you could see that the cost of a landing page is indeed $4,820. So this part seems to be working. So all of this code is going to be the starting point for our project. We got to this point from other tutorials where we actually build this all from scratch. But for this video, this is where we begin. We are going to take this app and then make it so that we can run it in the cloud. Anybody can run it from anywhere. And that's going to be what we need to do if we want to actually build this out into something bigger. Next, let's take a look at our strategy for how we're going to deploy this to the cloud. Before we start coding, let's talk through the architecture for this project, because I think it's important you see the whole picture end to end before you begin. Let's start with the RAG app that we just discussed. The AI service that we use for the embeddings and for the chat itself is going to be cloud-based already. For this, I'm using Amazon Bedrock. But aside from that, the app runs locally. The database is also saved locally. First, we need to add an API endpoint to this. We can do this easily by adding a FastAPI server that wraps the app and lets us call the app by using API routes. For the actual hosting, I want to use AWS Lambda to deploy this as a serverless function. If you're not familiar with it, it's kind of like a virtual server that only starts up when we send a request to it, and then it shuts down by itself. So it's extremely scalable and cheap since we don't have to pay any hosting costs while it's idle. To make this work on Lambda, we'll also need to add a handler to act as an entry point. Lambda doesn't natively understand FastAPI's interface, but we can use this handler adapter to fix that. Next, we'll need to get it ready for deployment. Our app uses a lot of platform-specific binaries, maybe not directly, but in its dependencies. This is challenging because some of these dependencies are sensitive to things like OS version, Python version, and even CPU architecture. And what ends up happening quite often is that apps that run perfectly fine on your local machine ends up breaking in strange ways after you've deployed it and try to run it in the cloud. So how can we make sure that this will be able to run anywhere? Well, the standard solution for this is to turn it into a container image using Docker. This will create a consistent virtual environment that you can deploy anywhere, including AWS Lambda, and you're pretty much guaranteed that it will run without any unexpected surprises. Once we have the Docker image, we can then deploy this to AWS. We'll create a Lambda function that uses the image and an API endpoint so that users can have access to it. Note that the AI component is still external to this app, so that's why the arrow points outside of the box. The database is still going to be local though. We're going to copy all of its files into the image to be deployed with the rest of the code. To create all of this cloud infrastructure, we're going to write it in code using AWS CDK, and we can also use that to deploy it to our AWS account. Once that's done, we'll be able to access this app via a public API endpoint. Okay, so that's pretty much the architecture plan for this project. Now let's get started coding. First, let's create an API wrapper around this RAG application. We'll import FastAPI and create a new FastAPI app. Then we'll create a new API route to handle the query and generate a response using that query RAG function from our starting app earlier. I'm going to call this endpoint submit query, and it's going to take the query text as input and return this query response object, which contains the query itself and the answer. If we want to test it locally, we can also add a main function so that it spins up server on port 8000 when we run the script directly. Finally, to make this work with AWS Lambda, we're going to need to add that handler adapter that I mentioned during the architecture section. We're going to use this library called mangum, and it gives us a function to wrap the entire FastAPI app with it, turning it into a Lambda-compatible handler. This is the magic piece of code that will let us use AWS Lambda almost like an API server. So let's go back to our code editor to see all of that in action. I'm going to create this new app API handler file inside the source directory here. So not in the RAG app directory. The handler is going to use the app, but it's not going to be a part of the app. And for the first part of the code, I'm just going to use this to create a FastAPI server and just have it say hello world when we reach the endpoint at its root. After that, I'm going to import this query RAG function from our RAG application. So here, that's the app that we looked at the start. And I'll open it here just so you can see. And we have this query response data class and this query RAG function. So I'm going to import these and use this as part of our submit query endpoint. So now this is going to be how we run the application through the API. And it doesn't do anything fancy. It just takes this request, which I've defined here as the new model. And the request is just going to have a piece of string as the query text, run it through this function, and then just give us the entire response. Next, I'm going to be able to want to test this locally. So I'm going to add this main function to basically just run this app on port 8000 when I run this script directly. So now I'll be able to run this, and then the FastAPI server will come up. But before I test it, I just want to finally add this handler to wrap the app and make it work for AWS Lambda. When we run this locally, this is not going to do anything at all. This is just going to sit there, and we're just going to serve this app on its own. But when we put this application into AWS Lambda, this handler is going to be our entry point. And we don't really have to know what it does. It's just kind of like a magic adapter that makes Lambda understand how to route different queries to each of these endpoints. So once you have that code there, you can just go back to your terminal, and you should be able to just run the Python script directly, and you should see something like this. So this is now starting this FastAPI server on this local address. And if you go to the address, you could see that our default route is being used, and you could see the hello world being returned there. But if you want to see the rest of our endpoints, just type in /docs at the end, and you'll be able to have this web browser to view and interact with all of the available endpoints. So here is our submit query endpoint, and you can even click here to try it out. So let's put in a query text. How can I contact support? And then we'll press execute. And if you click back to your terminal with the FastAPI server, you could see that it's working in the background. And back in our browser, after a while, it should give us the full response with all the citations as well. And you can validate as well that it's getting the right pieces of information for us. So it's telling us that there's phone support available, email support, and even office hours and the time that is open from. Okay, so with this piece of code, we've now put our entire app inside of an API. Next, we just have to figure out how to deploy it. By the way, going back to our GitHub source code, I've actually created different checkpoints for each of these major chapters in the tutorial as well. So if you're working through this yourself and you wanted to just see a specific part of where the project is up to, for example, just then we looked at adding the FastAPI server, you find this feature prefix at each commit that is intended to be a major chapter. So this was the first one we looked at with the starting point of the project, and this is the one we added the FastAPI server. And all these other ones are features that we're about to see coming up in this tutorial. Next, let's see how we can get this into a Docker image so that we'll be able to run this consistently anywhere. First, we're going to need to put all of our code into one directory. So I've moved my source folder, my populate database script, and my requirements text into this image directory. Then we want to create a Docker file in this directory. So just go to new file, and a Docker file is basically just a file called Dockerfile. That's it. If you're not familiar with how Docker works, then this Docker file is basically just a set of instructions for how to build a container image. When we run this script, it has access to all the files within the same directory that it's in. So that's why we had to make sure everything we want to deploy is in there. For example, our Python application code and our database. Now in this case, I've just checked out this particular commit from Git, so it didn't have the database committed. And if you're in the same situation and you only have the PDF here, you first have to rebuild the database. So go into this image directory and then run this populate database command again. And once you have this Chroma database inside your data file, you should be good to go. And here's how we can start writing the Docker file. First, we select the base image. I'm going to use Amazon's base image for Python. This already comes with Python installed, and it's guaranteed to work on AWS Lambda. We then install all of the Python packages we need by copying this requirements text file into the Lambda task root. And this is going to be a location provided to us by this environment variable here. You don't have to set it yourself. This is included as part of the base image. And it's kind of like a working directory. We'll also expose port 8000 in case we want to run and test this container locally later on. After that, we can finally copy all of our code into the image as well. I want all my Python files and my database. I also want to preserve the entire directory structure. So back in my code editor, my Docker file currently looks something like this, but it's not quite ready yet. With every major project, you're likely to run into some very tricky technical problems that are going to be specific to the project. These are some of the challenges I ran into this project so far. First, the PySQLite 3 library that comes with our base image is outdated. PySQLite 3 is a database that is required by ChromaDB. And if you just try to run the image right now, you'll probably see an error like this. When we try to load our vector database, it's going to complain that our version of SQLite 3 is outdated and it will crash. The second problem is if we want to load our database from a local path, then it seems ChromaDB requires both read and write access to that path. In AWS Lambda, there's only one directory we're allowed to write to, which is the temp directory. So we're going to have to do a few hacks to solve these problems. First, we'll add this line into our Docker file so that we can install an updated version of PySQLite. But because PySQLite is a built-in library, installing the binary alone isn't enough. In our app, we'll also need to use this code snippet to replace the reference to PySQLite in our Python runtime. That takes care of the first issue. To solve the second problem, we simply have to copy all of our database files to the temp directory when we're running it in AWS Lambda. Now, since Lambda containers can stay warm and get reused for up to 15 minutes, we only want to make sure that we do this copy once. So we could just check first to see if files already exist in that directory. All right, now let's go back to our project and take a look at the code. So first, I'm going to add this install SQLite binary up here. And the order where you add these instructions matter because the Docker runs them from top to bottom and it tries to cache the layer of the image at each instruction. So all the stuff that I want to do once and rarely want to change, I want to add them towards the top. So for example, anything to do with installing my requirements or this PySQLite binary, I don't want to keep repeating it each time. I'll put it closer to the top of the app. And then instructions like copying the files, well, I might change the files quite often. So by putting this at the bottom, I don't have to repeat all these steps when I build the image again. Now, another thing I'm going to do is also add this environment variable, and it's going to be called isUsingImageRuntime, and I'm going to set it to true. So basically inside my Python application, I'm going to use this to check whether I need to use this version of the library or if I need to copy my database to that temp folder that I just talked about earlier. That's because sometimes I might want to be able to use the source code just directly as well, just from the command line, or maybe I'll use it as a part of another app later on. So that's why I have to give it a way to know if it's running inside an image or not, because I wanted to do special things if it is. Now back in our Python application code, we're going to go back to this get ChromaDB helper script. And if you remember, this one will basically initialize the ChromaDB for us as a singleton. A couple of changes here. First of all, I've created this get runtime chroma path, which will return us where that chroma directory is, depending on the runtime environment. So we're going to put this here because we want this to change. And then next, I'm going to add this isUsingImageRuntime Boolean, which we're going to extract from our image runtime environment variable that you saw earlier being added into our Docker image. But if it's not set, then by default, it's going to be false. So if I run this script directly from my terminal, it's still going to be false, and anything using this flag will be ignored. And here, I'm going to modify my get chroma runtime path to use this temp directory, as I mentioned earlier. And I think that if I run the Docker image locally, like on my computer, it's going to be okay as well, because all of these drives are kind of mounted locally to that Docker image environment. But when I want to run it in Lambda, I definitely want to use this temp folder because that's the only one I can write to, and I need write access for ChromaDB to work. And I might want to override this chroma path with an environment variable as well. So I'm going to set it to get chroma path, but it's still going to default to the same data/chroma that we had earlier. So that's not going to change too much. And now I'm going to check if we're actually using an image runtime. So if we're running in Docker or running in Lambda, we are going to replace the PySQLite library with the one that we installed as the binary. And finally, I'm going to have this helper function called copy chroma to temp. So I'm only going to use this if we're inside an image runtime. So this is if I run it a Docker image locally or if I run it on Lambda. And this file doesn't do anything fancy. It just checks if the path exists. It creates it if it doesn't exist, and then it copies everything over from where the files are originally to this runtime path, which is going to be in this temp directory. So that pretty much covers all the changes we need to make to get this working as a Docker image. Before we start writing the infrastructure code for this app, you might want to see if we can get it built and tested locally first. Run this command to build the image. Also, notice that I'm forcing the platform to be AMD 64. That's because I'm running this on an M1 Mac, which uses ARM 64. But that doesn't play quite well with our SQLite binary, so we have to use this AMD 64 platform. Next, we'll need a way to supply our AWS credentials to the image. Create a file named .env in your image folder. And for the AWS region, I recommend you doing everything in US East 1 or US West 2. Because not all AI services are available in the other regions yet. And then don't worry about the table name variable yet. We'll come back to update that later once we start using a table to store the results for our app. As for the rest of the keys, just replace it with whatever your AWS credentials are, but never commit this file to GitHub because if you do that, then people will be able to see your AWS credentials, and you don't want that to happen. Once you've built the image and created the environment variable file, you can then use this command to run the app. This will spin up an API server, which you can then access via port 8000 on localhost. You can inspect and test the app visually by going to the docs endpoint in your browser as well. Of course, you could also send a local API request to it directly using a tool like curl. So let's go back to the code editor and do all of that. And here you'll see I provided a sample.m file already for you to use as an example. So what you want to do is copy this over and then just rename it to .env. And then after that, you want to replace these two to match your AWS credentials. If you don't know how to do that, just stop this video and have a look first how you can get the access key ID. I'm just assuming that you already know that for this video. And once your end file is updated, we're ready to build this Docker image and try running it in our terminal. So just go back to your project in the terminal and then go into that image directory. And then you can run this command to build the Docker file. And the first time you build it, this is going to take a little while because it's going to have to install and download everything. But as I mentioned earlier, each of these layers get cached. So the next time you build it is going to be a lot faster. Once the image has finished building, you can use the command I showed you earlier to run it as a Docker image on your computer. And if you want to know more about how to configure these Docker commands, like what this port does or what this M file does, I recommend you looking up the Docker documentation or watching a tutorial video on it. But anyway, this is going to be enough to run our app locally. And here it's already running, and you could see that we have a URL like before that we can access. So just clicking on that, I could see my hello world message. So I know that works. And then, of course, if I go to the docs endpoint, I see my APIs there as well. And I can use this too. Now, this is pretty similar to what we achieved with that FastAPI chapter earlier in the video. But the difference here is that now we're running it from a Docker image, which means that if we can get it to this point, we can pretty much deploy it anywhere. Because as I said at the beginning of the video, Docker images have a very consistent runtime experience. So if it runs fine here, you can be almost guaranteed that it's going to run fine on AWS Lambda as well. That makes it a lot easier to test and to debug if you want to build this out further. Now I'm just going to run Control-C to terminate this, this container because I don't need it anymore. Next, let's use AWS CDK to create all of the cloud infrastructure for hosting our app. By infrastructure, I'm talking about the actual Lambda function and the API endpoint you see here. You'll also need to have enabled all of the Bedrock LLM models that you want to use for this app, if you haven't done so already. And just to remind you again, if you're at any point in the video where you're confused about some of the technologies or the things I'm using, then I recommend checking out some of my previous videos in the description to first learn the basics. To begin, we first need to create a CDK project, but this can only be done in an empty directory. So we're going to make a new empty directory in our root project called rag CDK infra. We will go into that directory and then we'll use this command to initialize the CDK app. For this app, I'm going to use TypeScript as my language, but you can also choose Python. I just prefer using TypeScript because CDK is natively written in TypeScript, and I think the experience is a little bit better. In our application stack, we'll first need to create a reference to the image. This is the code to do it. We basically just point it to our image directory, which I have to use this ... because it's actually in the directory above our CDK directory. And then when we're about to deploy the app, it'll run the Docker file to build the image for us. So this basically just points us to that image folder that we've been working with earlier. Next, we'll create an actual Lambda function using the image. The code will look like this. You can of course configure things like the memory size and the timeout to your liking. We'll also need to grant our function the permission to use Amazon Bedrock for our embeddings and our AI calls. Finally, we'll create a function URL so that we can access the function from the internet via a public endpoint. And so that we know what this URL is every time we build the app, I'm also going to put this URL into a CFN output. So let's go back to our terminal and look at that in a little bit more detail. And if you've checked out this from GitHub at this checkpoint specifically, you might need to go into the rag CDK infra directory first and just run npm install to make sure that you get all of your dependencies. Back in your code editor, go to your CDK infra folder and go into the lib directory. And you should see a file like this. This is going to be the CloudFormation stack, which is kind of like a group of infrastructure resources that you want to deploy for this project. So first, I'm going to import a couple of dependencies that I'm going to need. So there's going to be Lambda and IAM access management policies. And the first thing we're going to do is create this image code. So this is going to be the Docker code. We're going to point this to the image folder, which is here. I think that all of these addresses are local to the actual project root itself, which is going to be the CDK infra project. But this image file is actually, a level above that. So that's why we have to sort of escape it out one level. And here the command is going to be what will be running as the Lambda handler. So we need to point it to that handler adapter function we've created in our app. So I'm just going to show you again exactly where this is. So we have our source app here. We have our app API handler, which is this name of the file. And inside this, we have this function, this object called handler. So that's exactly what this is pointing to. And as I mentioned before, we have to build this on AMD 64 architecture. Otherwise, our Python PySQLite binary will not work. Once we have the image code, we can create a function using this image code. So that's how we reference it. And you've got the memory size and the timeout as well. And you can change this if you need more timeout or more memory. But I don't recommend going less than this. And next, this is going to be the code that gives us a function URL endpoint. We don't really have to do anything much. We just add this and it's done for us. When you do go to production, you might want to put more authentication on this, but here we're testing it. So we're just going to put no authentication. And for the last line, we have to add the permission to use Amazon Bedrock. If you're not using Bedrock in your app, then you don't need this line. But this is because I'm using this app to call Bedrock directly. And by default, Amazon locks down all permissions, so you have to grant them explicitly if you want it to have access. However, if you're using something else, like maybe OpenAI as your API for the embeddings and for the LLM, then you might not need this line at all. And last but not least, I have this code snippet to make the function URL appear as a CFN output. So basically, when I build this entire app, I get to see this URL really easily in my terminal, and then that's how I know what it is, and I can go ahead and test it. So once your code looks like this, we can go ahead to our terminal and actually deploy this to our account. To deploy it, go to your terminal, navigate to the infrastructure folder, and then run the command cdk deploy. And if you're doing this for the first time, you normally get asked to validate any permission changes that are about to occur. So you can just go ahead and press yes. And once it's done, you will have this function URL output that you can just click and test. So this is going to be a public endpoint. So I'm going to go ahead and click that. And the first time you use it, it might actually take quite a while to load. That's because Lambda functions have this concept of a cold start, where if you use it and there's currently no Lambda functions running, it has to basically create a new one, download all of your code, and then run that for the first time. Now the function's going to stay warm for 15 minutes. So if I just close this browser and load it up again, it's going to be much faster. So you can see here, it pretty much loads right away. And the code start will depend on things like the size of your image, the size of the function itself, and yeah, just a couple of other things. That is a disadvantage if you want code starts to start up really fast for Lambda, but I think the trade-off is that it's going to be a lot cheaper because when you're not actually using it, you're not paying for anything at all. So that extra bit of latency when someone uses it for the first time, I think it's worth it. And if you do hit a very big scale, then more likely than not, you have enough users to keep Lambda functions warm, and then you won't experience the code start delay. But as you can see, this is now running completely online on AWS. And then I can go and test all the endpoints and do all of that stuff as well. So here I go to the docs, I see my submit query. I can open that and I can even try it out. And here I've asked my app, how much does a landing page cost to build? And I've got my response. According to the information, it's going to be 4,820. So that's our magic number from the PDF. So everything's all working properly, and this is now online. You could send this to somebody else who has internet access, and they'll be able to use your app. So congratulations, if you got to this point in the tutorial, it means your app now works at a very basic level. But don't stop yet, because there's still a lot of very important things we need to do next. It's very likely for an app like this that you'll want the ability to save all of the queries and its responses to a database. That way you can fetch them later if you wanted to. To achieve this, we'll need to add a database table to our infrastructure and modify our code to use that table. First, we'll create a database in our CDK app. I'm going to be using DynamoDB for this because it's really simple and really scalable. We have to pick a primary key, so I'm just going to call it query ID. And I'll also set the billing mode to pay per request. Generally, I recommend the on-demand pay-as-you-go model if you're just starting out or you're just building projects for learning. Because most of the time, the amount or the volume of requests you're sending to this is really small. You don't have real users, you're just building it out, and it tends to be cost effective or almost free unless you use, hundreds of thousands of requests. But even if you wanted to build this into a business, it still scales extremely well. Like you can use the AWS cost calculator yourself. It's probably going to cost you in the tens of dollars to serve millions and millions of requests per month. After we create the table, we'll have to go back to our Lambda function and pass in the name of the table as an environment variable so that our Lambda function can access it later. We'll also need to grant the function access to read and write data to the table. Back in our Python app, I'm also going to create a Pydantic model to act as a relationship mapper for the items in our table. This is where we can load the table name from and where we can also specify the fields and the data types. The class will then have functions like this to help us save and load data from the table using the AWS SDK in Python. We can go back to the API app as well and modify it to be able to read and write information from the table. So I'm going to do this by adding a new route called getQuery. Now let's go back to the code and add all of this stuff in. So here, first in my CDK stack, I'm going to create this DynamoDB table and make sure you have the imports as well from DynamoDB. So here's going to be my partition key and my billing mode, pay per request. In my API function, I'm going to add the table name as an environment variable. This is how I'm going to find this table later on in the SDK and then write or read data from it. And then finally, we're going to grant read and write data access to the function so that it can use the table. Now let's pop over to our Python code. So this is going to be in the source file inside image. I've added a new file called query model, and this is going to be basically just a relational item mapper for our table. You don't really have to understand what this code does. You could just go to my GitHub and copy it. It's not really, worthwhile to learn for this video. All it does is just gives us a typed data structure that we can use, in our Python code, but also some helper methods to write it to the table or to load it from a table. So nothing too fancy here, but just a couple of important things. This is how we get the table name. So this is the class that will use the table name from the environment variable that we just set in our CDK. And it's going to use the AWS SDK to actually create and write those items to the table. And you could see it here. This is where it creates DynamoDB client. And these are the functions that let us write items to the table and also get items from the table. For the fields, I've got a query ID, which I'm going to generate automatically using a UUID. I'm going to also record the time the query was created. Again, these are things that are set automatically. The query text is going to be the question that is asked to the AI app. And then the answer is going to be optional because it's going to start with not having an answer until we get the answer from running the app. The sources is going to be a list of strings. So this is going to be the citations. And finally, we're not going to use this yet, but I also have a is complete Boolean. So later on, when we ask a query, we don't have to get the answer before we store it into the table. We can have an incomplete query that's still in process. But anyways, we'll get to this. Now, back in our API app handler itself, we're going to have to make a couple of modifications as well. So here, this submit query endpoint, we're going to change this query response type to be the query model that we actually created. We're going to use that now. And then instead of returning a query response directly from our app, we're going to actually create a new query model object and write it to the table. So here I'm going to create a new query and I'm going to pass in the query text, the answer, the sources, and I'm going to mark is complete equals to true. Then I'll use this function to write it into DynamoDB, and then I will return this entire query. And finally, to be able to fetch information from the table, I'm going to add a new route entirely called getQuery. This is going to take the query ID as a string, and this is just going to use this query model to get the actual item. So once we submit queries, it's going to be saved. It's going to always be available forever, pretty much, I think. And then we can just use this to read information from the table. So if everything's ready here, we can go ahead and CDK deploy again. Once this is finished deploying, let's go back to our endpoint and test it again. So I've executed this query, which is to ask how much does a landing page cost to develop? And if I scroll down, I still get the response right away, but I also get the query ID now and a couple of the other items that we created as part of this item model. And the query ID is an important one because if we copy this and then we go back to our getQuery function, we can now try it out, put in the query ID, and this will fetch us the item from the table right away. So this is pretty cool. Every time we submit information to the table, we're going to see it get saved. And then if you go to your AWS account console and look for your DynamoDB table and browse your items, you should also be able to see all of your queries and items being created here. Now, if you want to be able to test this locally as well from your Docker image, don't forget to update that table name environment variable from our .env file as well. Now that we're able to save and load data, we're almost finished with this project, but there's still one very important problem we need to solve. Right now, we have a pretty big problem with this app. Our app uses AI, which can take quite a long time to execute. It might be 5 or 10 seconds right now, depending on the query size. But if you want to extend the app later, you might actually have really large prompts or complex logic, or maybe different steps in your application. This could increase your processing time to 30 seconds or more. Now that is a very big problem for two reasons. First, we can't go beyond 30 seconds with this architecture because that is a hard-coded limit on the API endpoint feature. Secondly, it's generally a bad idea to maintain an open HTTP connection for anything longer than a few milliseconds. It leaves your connection vulnerable to interruption or network outages. It's also probably a bad user experience, having to wait that long for any kind of response. So the solution here is to make our API asynchronous. This means when we execute it, we can get a response back right away, but it doesn't have the results of the query yet. It just has the ID of the query. We'll put the query item into a database and then set it to a pending status. Then we'll kick off a second Lambda function to work on this query in the background. I'll call this the worker function, and the worker can take as long as it wants, because right now we have the query ID and we can just keep checking to see when it's done. Sure, this doesn't make the overall use of the application faster, but it does mean that we're more responsive and we don't have to maintain an open connection the whole time. After a while, the worker should be finished. So we'll use a separate API route to get the results of the query. This one just looks directly at the database. If the worker is done, we'll also see the results there. Otherwise, we'll just get a status that the query is still in progress, and then we can check back again later. To implement this, we'll have to split our Lambda into two separate functions. The user will only interact with our API function, and that will trigger an asynchronous execution of the worker function in the background. Both functions will need to have access to that database table we created earlier, so that's how we'll store and communicate information back to the API and then back to the user. And since the 30 seconds timeout is actually a property of the API endpoint itself and not the Lambda function, we can now configure the worker function to have a much longer timeout. I think up to 15 minutes even. So this is very good if we have a large task for the worker to perform. Now, for the simplicity of implementing this, I'm actually going to use the exact same code and the exact same Docker image for each of these two functions. I'm only going to modify the entry point to the function. To implement this, I'll start by adding a new handler file to our project code. This would directly take a query dictionary object as its input. So this is going to be the same item as a query model before. We're just going to serialize it to a Python dictionary. We'll reuse this RAG application query RAG function to process the input synchronously. And when it's done, we'll flip the isComplete boolean to true on the item and then save the item back into the database. Then back in the other part of our app, the API handler, we're going to create a new helper function that we're going to use to invoke this second worker Lambda function. So by setting this invocation type to event, the call will become asynchronous, and this function will actually return right away. The second function will start doing its work in the background. It's not going to wait for it to finish. Once the Python code changes are complete, we'll also have to update our infrastructure code to make it all work. We're going to create an image from the exact same Docker file, but we're just going to update this entry point command to use the new worker handler we've just created. So that's going to be the new script. And then similar to the first function, we're just going to create a new Docker image function using that image. We'll also have to give it the environment variable for the table because this function also needs to know about the table. Our API function also needs to be updated so that it knows the name of this worker function because we're going to need that name if we want to invoke it from inside this function. Finally, we'll have to make a couple of modifications to our permissions. The worker function will also need access to the database table, but we also need to grant the API function the ability to invoke the worker function. Also, don't forget to switch the bedrock permission to the worker function, because that's going to be the one that needs to call bedrock now. The API function only needs to interact with the database. Now let's go back to our code editor one final time to put all of these pieces together. So in our Python source directory, I've created another Python script alongside my API handler, and I've called this one app work handler. The first thing we're going to add to the script is the handler function itself. This is going to be the function that this first function will invoke directly. And it's going to have this event object with it. So this is going to be a dictionary. We can pass whatever we want. The first thing I'm going to do is I'm going to use my query model item and basically just turn it back into a structured data type. So we're just going to explode this dictionary object here, and this will help us initialize the query model with all the information we want. Next, I'm going to create this function to invoke the actual RAG application. It's going to take this query item as its input, and here we're going to call that query RAG function that we imported from our actual application itself. After that, we actually want to put this back into the database. So this query model is going to be updated with all the responses we get from this. And this is synchronous, so it doesn't matter if this takes, a couple of seconds or even a few minutes. This code is just going to stop here until this is done, and it will continue. So we're going to add all of these answers at the sources and then flip this complete flag to true. So now we know that this item is finished. We'll then use this helper function to save it back into the database. And I think this is pretty much all we need. But if you want, you can also print a confirmation that the item was updated, and you can also return it. But I don't think we really need to do these two lines. It's not going to make a difference to the app. Once you have this function, all you have to do is just add it here to the handler to invoke the query. If you wanted to test this locally, you can also create a main function and a helper function here as well, just to test that this part on its own works. I did this originally when I was creating the app, but I can tell you that this already works, so you don't really need this part unless you would just want to run this file directly. Now let's go back to our API function to modify it so that it can use this worker function asynchronously. Right now it's synchronous, and I might want to keep that for testing purposes, or if I want to have a synchronous model of execution. So I'm not going to get rid of this code. Instead, I'm going to see if the worker Lambda name exists in my environment. So I'm going to use this to load the name if it's there. And if it is there, I'm going to take a different path. If it isn't there, I'm just going to do things exactly the same way as before. I'm going to write the item directly after I get the results and then just return the item. But if it's not there, I'm going to save the item first. This will create an entry in the database even though the response is incomplete. And then I'm going to create a helper function to invoke the worker in the background. This is going to take the actual query that I created here, and we're going to start by creating a Lambda client. We're going to first have to serialize the actual query itself into just a general JSON dictionary. So a string key mapping. Luckily, I think that Pydantic has a helper function to do this for us, so we don't have to do this ourselves. We just do model dump. And once we have this, we can add this as the payload. So we'll invoke this worker Lambda function using the worker name we loaded from the environment. We'll set it to an event invocation so that it's asynchronous, and we will supply it this payload, which is basically our query model. It also contains the query text. And at the end, you can print the results if you want, but you don't really have to. So this is just for debugging. And now we'll go back up to this block of code, and we will invoke the worker if the Lambda name exists. In either case, we will want to return the query. So what happens in the asynchronous path is that we get here, we create the query. If a worker function is attached, we will add it to the table first, then we invoke the worker. This doesn't wait for it to finish. This will run in the background. And then we're going to exit out of this block and just return the query. And in the query, we will have the query ID. So now, from wherever we called it, we know exactly what we need to call to see if the results have finally finished processing. So those are all the changes we have to make to our API application code. The final thing we have to change is our infrastructure code to wire this all up together. So go back to your infrastructure code, your CDK, and first we're gonna create a new Docker image using that other handler that we just made. So the code is pretty much identical from our API image itself, except that we changed the handler so that the entry point is going to be this app work handler handle function instead of the API one. And once you have the image, you can use that to create the actual Lambda function for the worker. And I'm going to set this one to a slightly higher memory and a slightly higher timeout. And you can set this to whatever you want as well. The function will still need to know the table name, so we will keep this environment variable here as well. Now back to our API function, it needs to know about the worker. So I'm going to supply the name of the worker as this worker Lambda name environment. And then again, if you remember, we load it up here at the top of this API app. Then we'll scroll all the way to the bottom and then just fix our permissions. So we'll need to add the read-write data to the table. We'll need to grant the invoke ability to the API function so that it can use this worker function. And then we're going to update our Bedrock permission so that it's now the worker function that has access, because this is going to be the one that actually calls Amazon Bedrock. Once this is completely deployed, we're ready to do our final testing. So let's go back to our URL endpoint and then go to the API Explorer. And this time we're going to submit a new query. So let's try it out. And the query I'm going to submit is, how can I get support? Let's execute this. And see here, this returns it right away. We don't have to wait at all, but we don't have the answer yet, but we do have the query ID. So let's go ahead and copy this and go back to our getQuery API. And I'm just going to use that here. And now when we get it, you can see that the answer has been populated and the complete flag is set to true. So even though we don't get the answer right away when we submit it, we do get a very fast response. And this is really good if you have a process that takes a really long time to finish, or you just want a more reactive experience. We can check the answer as well to make sure that it's accurate. And you can see here that it is probably accurate. It's got email support, phone support, and office hour support. And if we go back to our PDF, I'm pretty sure that all this information is pulled directly from there. Yep, so you can see on this page of the PDF, we have email support, operational support, and office hours on these times. Okay, so I think with this, we can be pretty sure that our app is working quite well. It's been deployed to an endpoint. It is asynchronous, so it's not prone to interruption or to network outages if we have a really long query, and it's also just a lot more responsive. It also saves all of the information that we have into a table so that when you use it a lot of different times, you can actually go back and look at the different answers, or maybe even do a list of the most recent questions and answers. Congratulations if you've made it all the way through to the end of the project. This was a very challenging project to build, especially if you've never done anything like this before. So if you got this all to work, then give yourself a big pat on the back. You're probably on your way to building the world's next big AI service. I hope you enjoyed this video, and if you have any questions or feedback, just please leave them in the comments. If you need help, then check out the GitHub link in the description. You can browse the code there and even use the various checkpoints in the commits to map to different points in this video tutorial. You can also post issues on the GitHub and I'll respond to them as well. If there were any parts of the project that you felt you wanted to dive into a little bit more, then check out some of my previous tutorials on this channel. This includes things like setting up AWS, building a RAG app from scratch, how to use Docker, and how to use AWS CDK. Otherwise, thank you for watching. See you in the next one.